few times, been to Winnipeg 5 or 6 times, but I've never actually been to this campus. So it's a real pleasure to be here for the first time. The weather is not too different in London. This was taken just last week. And this is the Robarts Research Institute where I live. And our MR Center is a wing that is attached right there. Using Google, it's a little bit easier to see. So we have a 14,000 square foot MR Center with 3 magnets attached to the Robarts Research Institute. This is the London Health Sciences Center North Campus. Many of my colleagues are in the Brain and Mind Institute, which is right over here, for another 1.5 years, and then there's a 7-story tower going up right here at the moment where we'll be moving to. So we're a little more compact. You guys are spread out quite a bit. It's really nice to be able to have code coverage from the hospital, even though we're part of the university. We can borrow MR techs and things as needed as well. So we have 3 MR scanners in my lab. We have a 3D Prisma, which is the first customer-delivered Prisma in the world, 3 years ago now, I guess. We have had a 7T human MR system for 9 years, and we've had a 9.4T 31 centimeter bore animal system as well for just over a decade. And all of these systems rely on something called RF coils, radio frequency coils, both to transmit and receive important signals that are part of the MRI acquisition. And I'll explain all of that to you in a minute, because I imagine most of you may not actually be familiar with that. So that'll actually be half of my talk. So these are all coils that are built in the lab for various things. This is a human 7T coil. This is a macaque monkey coil for the 7T. And these are it's a transmit receive coil for marmosets in the 9.4T. They're all built in-house. It's a major part of my research program as the major engineering focus. And so I'm going to tell you a little bit about them. And we're in the wrong, there we go. So, most of what I'm going to talk about is the work on the 7T system. And the 7T system is actually one of only 3 in the world that is sort of specifically designed for head-only imaging. So it's a smaller bore. It's actually a similar size bore to a clinical scanner, but then it has a head-graded insert, as I'll show you. And that allows you, basically, it's a short magnet. My knees are at the edge. So for 7T standards, it's actually very small. It has very powerful gradient coils. It has an RF front end, which allows parallel transmit and receive. And I'm going to talk about that quite a bit. And as I mentioned, all our coils are homemade. So let's start with a little bit of an educational digression. So MRI requires a number of things that generate magnetic fields. So the first of those, and the biggest, is the magnet. And these are superconducting magnets, and they generate a very homogeneous, very hopefully static magnetic field. And this is what we use to polarize the nuclear spins. So typically in imaging, we're using water protons. And that's all the data I'm going to show you today. But there are many other nuclei that you can use to do MRI or NMR. So when you have this very fancy, very expensive, very heavy main field, and you put a human head in it, you actually distort the magnetic field. And so something called shim coils are used to actually try to shim out the effect of the object that you've put in to make it as homogeneous as possible. Won't talk about that today. Gradient coils are actually used because if you've got protons in a very homogeneous field and they all resonate at the same frequency, That makes it actually very hard to do imaging. So you actually need to impose a spatial dependence of frequency and or phase on those spins in order to encode them in space. And that's what the gradient coils do. And if you've ever been in an MRI scanner, you've heard the bang, bang, bang noise that it makes. Essentially, it's a glorified loudspeaker. And then there's the RF coils. So the radio frequency coils are used both for transmission and reception of the NMR signal. And that signal, in our case, is going to derive from a brain full of protons. So let's look at some simple basics. When you put a diamagnetic sample, so tissue, water, brain, parts, whatever, into a strong magnetic field, approximately 0.3 thousandths of a Tesla percentage per Tesla of those spins will actually align with the magnetic field. So it's not like you get magnetized and get sucked in. It's a very, very small fraction of the spins that generate a net magnetization. That magnetization is oriented, we call it along the z-axis, so that's the direction of the main magnetic field. So here is a vector made up of millions of spins pointing along the magnetic field. And we can perturb that magnetization using a radio frequency pulse. And when you do that, there you go, you can tip the magnetization down into what we call the transverse plane. This is the xy plane. It's perpendicular to the main field. And then you turn off the radio frequency pulse, and the magnetization wants to go back to its equilibrium. And so radio frequency is used to tip this to begin with, and then you listen to the very small signal coming back. And that signal has the information that gives MRI images its contrast. So we won't wait for that. So this very simple equation, called the Bloch equation, is sort of the simplest description of the evolution of the magnetization in a magnetic field with relaxation times T2 and T1. I'll quickly explain those to you. So this B is the main magnetic field, as well as the magnetic field that comes from the radio frequency pulse. So I mentioned that we use gradients for spatial encoding, just to show you what we have. So this is why it's a head-only system, because even the bore is very big, but the gradient has an inside diameter of about 40 centimeters. This is a very powerful gradient system, so it allows us to do a lot of very interesting MRI things, which I won't really talk about today. I'll just keep this more on engineering. So the important thing is, as I mentioned, you perturb that magnetization into the XY plane. You can encode one direction in the plane, or in any direction really, with frequency. So you turn on this gradient waveform, and it imposes a linear field dependence on the spatial frequency. You can also change the time or the amplitude that gradient is applied, and you can encode phase. So what you end up doing is you end up collecting Fourier space representation of the object. And by doing an inverse Fourier transform, you actually get the image. The important thing is, in MRI, you actually acquire the data in Fourier space, just like radio astronomy and a few other things. And then you just do a Fourier transform in the simplest sort of manifestation to get an image. Just for you students, particularly who are looking for careers, the control of all the pieces, the gradient waveforms, the RF waveforms, and so on, is controlled with a computer program, usually written in C, that's called a pulse sequence. And the two things I'm going to talk about are RF transmission and RF reception, but there are all kinds of ways of traversing K-space that are controlled by these variables. And if you are fluent in this kind of physics and programming, I can guarantee you a well-paying job anywhere you want to live for the rest of your life. So keep that in mind. So, as I mentioned, the job of the RF coil is twofold. You need to excite the spin, so that's the transmit function, and you need to detect the NMR signal, which is the receive function. You can do this two ways. The same coil can be used to transmit and receive, so we call that a transceive coil. Or you can use one coil to transmit and another coil to receive. And that actually gives you more flexibility. So we'll talk about both of those. But almost everything you need to know about the fundamentals of RF coils, signal-to-noise ratio in the NMR experiment, and so on, was developed by a guy who lives in Winnipeg, Manitoba now, by the name of David Holt. He worked at the NRC for many, many years, in Oxford early in his career. And this paper is one of the most cited papers in magnetic resonance, and it covers off a lot of the basics of signal-to-noise ratio, B1 fields, reciprocity, and so on. So, this RF perturbation, in the simplest manner, your RF coil is a tuned circuit which resonates at the frequency that the protons are resonating in the magnetic field. This is the precession frequency that you will experience when you tip those spins into the transverse plane. So I'll show you that diagrammatically. So we have this tuned circuit, which is perpendicular to the main magnetic field. And we can apply an oscillating field at a resonance frequency that, for example, at 7 Tesla, our human scanner big frequency, is 300 megahertz. So if you apply a field like this, it can actually be, that is essentially an oscillating vector. As the current goes back and forth, you generate through the Biot-Savart law, something going back and forth in the plane. You can rewrite this as two currents, one oscillating with a cosine in the real component and a sine in the imaginary component. And the total magnetic field, which is in the Bloch equation, that B, M cross B term, is governed by this. It's the static component in Z and this oscillating component in XY. So if we substitute this into the Bloch equation, what you see is that there is a torque applied to the magnetization given by the effective magnetic field that the spins see. So this is the sum of the static field and the RF field. And if you do the little magical thing of making this RF field oscillate at the correct frequency, the so-called Larmor frequency, then, in fact, it's even simpler. During the RF pulse on resonance, the protons experience a torque, which is M cross B. So protons want to precess perpendicular to that B1, which is the transmit field. So pictorially, what does that look like? So this spinning thing is the so-called lab frame. The static frame is what we call a rotating frame. It's easier to think about things in the rotating frame. Here is a B1 field that we are applying perpendicular to the static field. And if we leave it on for a time, that causes the magnetization to go from here to here. It's a 90-degree angle. We call that a 90-degree pulse. Or you could have a 180-degree pulse, and so forth. So the requirements for a transmit RF coil are straightforward. We want uniform excitation over the whole sample. That means we want a constant amplitude for the magnetization across the entire volume. That means no matter where you are in the head, if I want a 90-degree pulse, I want to get a 90-degree pulse, not 60 here, 110 here, or something else, because then the magnetization that you detect and the contrast mechanisms that you generate tend to run into trouble. The other thing we want to do is if I apply, as in the previous diagram, a B1 on, let's say, the x-axis, then I want all my spins to tip onto the y-axis, not y plus 20 degrees or y minus 20 degrees or something like that. I want them all to be in phase, so that when I do subsequent manipulations to my magnetization, all the spins are doing the same thing. So that's the transmit side. So the receive side, same thing. So we've tipped the magnetization in the XY plane, and now you can think of it I hate to say this, but as a rotating bar magnet. So this rotating bar magnet, of course, will generate an EMF in an RF coil that is suitably oriented, so that is perpendicular to the field, as I mentioned. And the signal in the transverse plane does this, and it decays over time, and the signal is also growing in the Z direction. So this decay rate is T2, and this decay rate is T1. And that signal, T1 and T2, they differ in tumors, in flowing blood, in gray matter, in white matter, and so on. So that's where the differential contrast in MRI comes from. Okay. Important thing is you use typically a kilovolt, thereabouts, to actually excite the spins, but you're detecting a signal that is of the order of millivolts, maybe a volt if you get the signal from the whole brain. So it's much, much lower. So you need very high sensitivity in the RF coils and the preamplifier chain. And again, you want uniform sensitivity because if you have, let's say, a homogeneous flood phantom, for example, and you make an image, you want that to be flat. You don't want it to have intensity variations because those can give rise to diagnostic errors, for example. And as I mentioned, you want very high sensitivity. So the very, very simplest RF coil you can have is an LC circuit fed by a transmitter. All the amplifiers, power amplifiers that are used in conventional practice are 50 ohms. So you tune and you match this to 50 ohms. And when you transmit and receive with a small surface coil here placed behind the back of the brain, something like this is what you get. So surface coil will see somewhere between a radius and a diameter into the head. That's the extent of its penetration. And this is what a lot of original MRI was actually done with. So high sensitivity, but limited penetration. And you can describe the signal at low fields very nicely by the Biot-Savart law. So very simple first-year physics. Unfortunately, as you go to higher and higher fields, a number of people from Minnesota and the Penn State group and ETH and Zurich have shown over the years that it is no longer a nice circularly polarized signal and that is uniform in a phantom. So in fact, there are multiple things that are happening here. So B1 plus is the transmit field, and B1 minus is the receive field. And in the simplest manifestation at low fields, they're actually the same. So the principle of reciprocity appears to work. And so at 1.5 Tesla, so a typical clinical MRI scanner, if you put a coil back here, you get this nice homogeneous penetration, limited penetration, but it's symmetric. As you go to higher and higher fields, you see this gets very distorted. So at 7 Tesla, you can see that it's no longer symmetric. You actually get enhanced penetration on one side and reduced penetration on the other. This is due to a number of things, primarily the fact that you no longer have a circular polarization, it's actually an elliptical polarization. And secondly, you're actually now in an intermediate regime where you have to deal with near field and far field. So you actually have a traveling wave to consider. And so you spend $12 million to buy a human 7T scanner. You use a standard birdcage coil that might be used at low fields, and you get images like this. And you wonder why you spent $12 million, because they look like crap. Right? So this was the case when 7T first started in 1999. And it was still the case even till a few years ago. The biggest hurdle is RF homogeneity at 7T. So these should be homogeneous images of the brain, but you see dropout here. It's not due to susceptibility. It's actually due to RF inhomogeneity. Temporal poles as well. And it's not just the homogeneity that matters, because when you manipulate the spins with 180-degree pulses and 90-degree pulses and so on, the contrast that you generate depends on you having accurate flip angles. So here what's happened is you get nice gray-white contrast in the frontal cortex, but at the back where the RF homogeneity is bad, you lose that contrast. So it's not that the intensity of the image itself is lower, it's that you didn't get the flip angle you expected, and so you've actually lost contrast here. One of the major reasons for that is if you look at the wavelength at 300 megahertz, it's 13 centimeters. That's 7 in a human head. So with the permeability of the head, this wavelength is 13 centimeters, which is comparable to the dimension of your head. So you can think of this as setting up standing waves in the head. It's no longer, they're damped, and so you get all kinds of funny effects. But fundamentally, because you're in an intermediate regime now, you actually have to consider the object size, and you can't just assume that a plane wave is impinging like you can at 1.5 Tesla. So this is actually true at 3 Tesla in the chest cavity, for example. When you do cardiac imaging, you actually have the same problem. So at 3T, it's actually been common now to use 2 channels for parallel transmit. I'll talk about this shortly. So 7T has a lot of advantages in principle. You have high SNR because signal noise scales roughly as the field strength. There are all kinds of interesting contrasts. T1 gets quite a bit longer at high fields. People used to view this as a problem, but actually it's a benefit for many, many things, because you can label arterial spins and they'll actually go through the whole brain and come out without relaxing, which you cannot do at 1.5 or even 3T. So you can do wonderful things like non-contrast angio. Spectroscopy turns out to be really good because the spectral dispersion goes up. The fMRI signal goes up quadratically with magnetic field. DTI gets very much better. Nobody's actually proved that till yesterday, so I'll show you some images. You can image faster because you have signal to noise to burn, and then there are properties of the received signal because of the inhomogeneity that actually allow you to speed up the acquisition. And it gets you to the point where instead of having to do group studies, you know, N of 10 and N of 20, you can actually potentially do diagnostic work with N of 1. So, as I mentioned, RF hardware development is a major part of the basic science work that we do in our lab. These days, focusing a lot on transmit-receive coils, but I'll take you through the history of our thinking there. Full wave simulations, because you have to look for SAR, which is the power deposition essentially. You have to model coils. And there's a lot of black magic in RF. A lot of stray capacitances and things that until you actually build something, you can't always predict exactly how it's going to work. So this is my second career tip for you guys. The head of GE Healthcare and the head of Siemens Healthcare both made trips to London over the last 15 years. And neither one says there are enough RF engineers in the world to populate the MRI companies. So should you choose to go into a career building RF coils, I can also guarantee you a long, happy, and richly rewarding career. So I'm giving you 2 career tips: pulse programs and RF coils. So I'm going to talk about parallel transmit. Parallel transmit is a way to reduce the RF inhomogeneity. I'll take you through that, try to show you intuitively with some examples. But it's also expensive because it means you need multiple RF coils and you need multiple RF amplifiers, ideally with independent control of amplitude and phase of the RF pulse on each of those channels. You can actually combine parallel transmit with gradient coils to further flatten out the images using pins and KT spokes and KT points and techniques like that. I won't really talk about them today, but just so you know, there are additional degrees of freedom when you use parallel transmit. So the general idea is very simple. So this is a birdcage coil I showed you before, and usually you drive a birdcage coil with 1 channel. You can now, many of the clinical manufacturers drive it with 2 channels, and they adjust the phase and amplitude of one with respect to the other to try to do some shimming, as it's called. I'll explain that. But you can also imagine taking a bunch of surface coils. So here I have 8 surface coils, each with its own profile, and trying to excite the sample in such a way that you get uniform excitation. And the devil, of course, is in the details. How do you actually do that? So we've spent a lot of time, as well as other groups, in trying to figure this out. So the first thing to do is, in order to optimize the process, you have to be able to map the transmit pulses. We've integrated a workflow into our Siemens platform so that the MR techs can use it. They don't have to copy numbers. They don't have to run stuff on another computer with MATLAB or something. It's all actually done in the Siemens platform. And the way this works is you first map the relative B1 field. So very low flip angle, and we actually do phase modulation of the signal. So we're transmitting with all 8 channels, but we modulate the phase of 1 at a time. We do this sort of in a circularly symmetric manner. It takes about a minute. Once you know what the phases are, you can notionally set them to a simple so-called quadrature mode, so that they all sum in some large volume in a homogeneous manner, typically in the middle of the brain. And then you do an absolute flip angle map, in which you now calibrate the absolute B1 field of this summed signal. And then this is all reconstructed and loaded into the parallel transmit chain, and 2 minutes after you started, you're ready to go. So pictorially, what does that look like? So here are a bunch of relative B1 maps. So this is a profile of a bunch of individual coils. We set that to some circularly polarized mode. So basically, if you have 8 channels, they're set into 360-degree divided by 8 increments. And the phase increments all the way around. So that gives you a pseudo-homogeneous image. And then you calibrate that. Once you have the maps, you can look at the flip angle distribution, you scale that, and away you go. So this was work that Andrew Curtis, a former student of mine, who now works at Synaptive in Toronto, developed. And it's quite effective. It can take images like this and make them look like that. So all you've done is you've shimmed the B1 field. So you mapped it, and then you adjusted the phases to give you the most homogeneous field. All of a sudden the temporal poles and the frontal lobe and everything actually show up. So the B1 shimming is actually also run on the Siemens host. Those of you who use any clinical platform know how unhappy clinical vendors are when you start running programs and installing programs on their hosts. But here we have Siemens' permission. So it actually takes the volume adjustment. So once you've planned your volume for your scan, this is actually taken. That information goes into optimizing the B1 plus over that region. Then there's a GUI that shows you what your shimming result will be, and then you automatically load it in. So oddly enough, so there are about 67 T-scanners in the world, and we are the only site in the world that exclusively uses parallel transmit. We're also probably the only site in the world that routinely uses our 7T on patients. And we believe that without parallel transmit, you just can't get the homogeneity you need to be diagnostically useful, even in an experimental setting. So this all sounds really simple, right? So you take a bunch of coils, put them around the head, you transmit with each of them, you make a map of how much power it takes for each one, and you have your image. It's very simple. Well, life is never simple. So this is the first problem. So if you take a single tuned circuit, you put either drive it with a spectrum analyzer or put a little sniffer coil on it and couple to it, you'll see that if it's tuned at 297 megahertz, that's our resonance frequency at 70, you get a nice resonance. And life is great. This is the simplest possible surface coil. Unfortunately, when you put 2 such coils together, you get mutual inductance between the two, and the resonance splits. And you no longer have an efficient transmit or receive coil, because the sensitivity at the resonance frequency that you want is completely shot. So that's a bit of a tragedy. And a lot of work in our lab has been aimed at trying to get around this, and I'll take you through some of that. We have a second problem, as I mentioned. So we have many benefits. This 70 is light, it's only 28 tons, compared to 40 tons or more of some. We have no iron shield because it's actively shielded, so that saves you another 300 tons in iron. But the deficit is the bore is quite small. So this is 40 centimeters inside the gradient coil. So we have to fit all of our RF coil technology within that 40 centimeters, plus leave enough space, i.e. about 22, 23 centimeters for the head. So it's very high, dense, compact RF array that needs to be built. So this problem was solved by Pete Romer on the receive side many, many years ago, in a very classic paper called the NMR phased array. And that works because you can manipulate the input impedance of the preamps that the receive coils are connected to. You can effectively open circuit them. So you can reduce the amount of mutual coupling between those coils. That doesn't work for transmit coils because transmit coils use transmitters that are all 50 ohms. And yes, you can change that. You can build your own custom ones and so on. The rest of the world isn't following that trend. So everybody is using 50 ohm transmit amplifiers right now. The loop arrays, so taking any configuration of loops and putting them around a head or a body, is actually quite finicky in terms of trying to tune these and decouple them and so on. You don't have to use loops. You can use microstrips and strip lines and TEM resonators and so on. They're a little easier to decouple because they're separated in space to a certain extent, but their transmission efficiency is not so good. And then there's some techniques, in fact, Cartesian feedback, which was developed here in Winnipeg, that allow you to actually decouple on the transmit side. They're actually quite clever, but they don't work well with RF shimming because they actually manipulate the phase of the RF. So you can't superimpose the phase you want on the PTX system when you're already imposing a different phase to try to decouple the systems. So a little bit of a conundrum. So for many years we've been developing, well before this paper, we've been developing or modifying approaches. And this was back in 2010, featured on the cover of MRM, a comparison of a method where you can take two coils, and if you overlap them by a magical amount, typically about 10 to 15% of their diameters, the mutual inductance is null. So you probably learned that in first year engineering, first year physics. We showed a technique that allows capacitive decoupling of coil elements for transceive and transmit coils. And then we also had the stupid idea, well, it didn't seem stupid at the time, but of putting an RF shield around each coil, because then the flux from one coil couldn't thread the other coil, and therefore they weren't decoupled. I'll show you why that was a stupid idea, but it had some benefits. So here are the three: geometric decoupling, capacitive decoupling, and let's call it shield decoupling. So this is the transmit efficiency. You can see that the efficiency for the shielded coil with different insets, the height of this coil within the shield, is really awful compared to just plain old geometric decoupling. And the problem with geometric, any of these, is that the best you can do is nearest neighbor decoupling. You can't do next nearest neighbors, or you can't decouple for something that is physically across the coil. So one coil here and one coil here will talk to each other. So, there are limitations, but this overlap design works reasonably well, and that's what a lot of people have used. And all vendors now use this approach. on the receive side, so if you use these for transmit and receive, again, you see the same thing. You have the highest signal-to-noise ratio for the geometric decoupling case. It's not great for the two shielded cases, so these are scaled to the same intensity. So I just want to make a point. Again, this is a teaching moment for the students. So my student, Rob Pinkerton, first developed this capacitive decoupling technique for transceive coils. We published it in 2004 and 2005, and we filed a US patent at the time. That patent was actually not granted till 2012, long after Rob had graduated. And of course, nobody in Canada wanted to buy it or commercialize it or do anything, so it was sold to Siemens last year for a good chunk of change. So, when our governments and our political masters want us to patent everything and it's magically going to turn into benefits to all mankind, well, actually it takes a really long time and it may not actually benefit Canada, for example. So here's the capacitive decoupling, and here this is a 6-channel array. You can see 6 channels. You can actually do capacitive and overlap. So we, in this paper, describe the first coil that actually allowed 3D transmit and receive. So this allowed both receive acceleration. I'll talk about that later, and I think Scott's going to talk about that tomorrow quite a bit. But you could also separately shim sort of the lower part of the head and the upper part of the head, if you like. And that has some benefits because the RF solutions lower and higher are actually different. So if you have to shim the whole thing, it's a little bit of a compromise. So this worked pretty good, but if you look at these SNR maps, you see that they suffer at the top of the head. It's good in the middle. If you look at an axial slice in the middle, it looks pretty good. If you look at the flip angle maps, it's not bad. High in the middle, fairly homogeneous in a symmetric manner. So what can you do? The signal to noise is usually proportional to how close the RF coil is to the object. You really want tight-fitting coils as much as you can. And a cylinder is not tight-fitting at the top of the head. So we took our shielded design and we cut the top of the shield off, and we just left a guard ring essentially around it, made it somewhat less lossy. And that actually allowed us to get relatively high signal to noise at the top of the head now. So this is the same images you saw from the B1 shimming example. So this was a 16-channel conformal array, so the head goes in here. It's good right just to the top of the forebrain, and it's good all the way down into the C-spine. So pretty good. And notice that this is just because of shimming. This is nothing else. So the deep brain structures and the C-spine all appear when you shim properly. So again, this is a 3D shimming coil, so it actually has 3 rows. So it allows you to optimize the shim spatially. And it's just shimming that gets you from here to here. So if you look at one slice in the middle of the brain axially, or one slice in the middle of the brain coronally, these are the sensitivity profiles of each of the coils in that close couple element. Okay? And you can see that they have different sensitivity profiles. Different coils contribute in different manner at different points in the brain. So you can actually utilize that fact to undersample your case space when you do MRI. So you can actually skip lines of case space. And skipping lines of case space allows you to save time. And the reason intuitively that this works is because you know where each of those coils are. So you have some preconceived notion in a least squares sense or any kind of mathematical sense of where the signal from that coil is coming. So by undersampling, you normally would get an aliased image, but because you know something about where each coil is in space and what its sensitivity function looks like, you can, to a certain degree, unpack that aliasing. You can't just arbitrarily do that, but you can do that to a certain extent that depends on coil geometry and in fact magnetic field that you are working in. So using that same coil, there's a metric for accelerated acquisition, and it's called the G factor. So the G factor, this is a very confusing slide, I'm sorry, because it's actually plotted as inverse G factor, but the numbers given here are G factors. So in the perfect world, when you accelerate, your G factor would be 1. That means the acceleration introduces no extra noise into your reconstructed image. And for using that coil at 2 by 2, so that means speeding by a factor of 2 in 2 phase encode directions, for example, you get very close to that. So that's quite remarkable. You can speed up your image acquisition by a factor of 4 at 7t and not take an SNR hit. So that's quite stunning. But the minute you start going to higher accelerations, it all falls apart very quickly. So the only way to accelerate well is to have lots and lots of little coils. Okay, so that each coil has a very small spatial sensitive area that it's spatially sensitive to. And that's how you can unfold these things. That means you need lots of receive coils. Well, we have 8 transmitters, and if you run it as a transceive coil, well, that means you have only 8 receivers as well. You can play certain tricks with bucket matrices and other things, but fundamentally, you don't have a lot of coils to play with. But almost any modern clinical scanner will have a minimum of 32 channels. We have 64 on our Prisma, for example. We have 32 on our 7T. So we can pack in a transmit array and nested inside a receive array. We can make this a split design. So this was the first 7T coil in the world that actually allowed a patient to lie on a table and lie back into a coil. Until this point, all the vendors that sell these things had the patient lie on the table and then shimmy up into the coil. And we do a lot of patient studies. I'll tell you, patients don't want to do that. So we do a lot of longitudinal studies, which means we're counting on patients to keep coming back over and over again. So if you can't make it comfortable for them, they will not come back. So Kyle Gilbert here designed this coil with 32 receivers and 8 transmitters, which allows people to actually sit in. And the preamps, there's not enough room for the Siemens preamps in this particular design, so they live right behind the coil. So we have to think still about, now it's a real problem. So you got a lot of copper, all tightly coupled to each other, a lot of tuned loops, all tightly coupled to each other. And we need to decouple the transmit from the receive, and we need to all the receive coils from each other, and all the transmit coils. So we're still on this path of trying to figure out how to do this. I'll take you through some more examples. So we developed a tool, so I showed you this. We developed a technique called the magnetic wall. The magnetic wall is a strip, I'll show you the details in a moment, that goes between any 2 coils. And actually, you can think of this as a ladder filter. So you have 8 coils, so that is a network. That is a ladder network. And you can actually stop the propagation of an EM wave through that network if you design this strip with certain resonant properties. So these are called frequency selective surfaces. They're used in cell phones, and they're used in defense. So all the radar invisible planes are coded in these things, tuned with microwave frequencies. In fact, when we first got a US company to build these, they wouldn't export them to us because we had to get a defense license. So we found a guy in Mississauga who would make it for us, so much easier. So this is what those look like. So they are loops tuned roughly to the resonant frequency. They couple to each other. So this is Ian Connell who developed these and published the theory in this paper and a back-to-back paper, actually the reduction to practice. So with this kind of technology, you can actually decouple arbitrary arrays. So here's an array of 4 coils that is decoupled something to the order of minus 25 dB between. You can't decouple that any other way as a transmit array, except I'll show you how you can. But until this point, you were not able to do this. So these are 2 very sort of deep mathematical papers involving CST microwave studio simulations. I won't have time to go into the details, but the concept is not all that complex. So here is a multi-port model. So these are the transmit coils. And then here are a bunch of inductive loops. So these are the little frequency selective surface loops. You can model all of that as an equivalent network. You can set up the impedances. You can measure them. And then you can actually optimize to find out what these Zs should be. Once you know what the Z should be, you can go into CST or SPICE, and you can design the width and the length and the number of loops and so on to actually give you that impedance. And so this is what that coil looks like. So the 32-channel receive on the inside, magnetic walls separating 10 channels in this case. This was when we had a variant system which had 16 transmit channels. And you can simulate this, and you can look at the heating, and you can see that the magnetic walls don't actually give rise to any additional heating in the object, and you get nicely decoupled field patterns. So this seems like we've solved the problem, except that each of these strips is actually a little bit lossy. So this might not come as a surprise to some of you, but it's about 0.3 to 0.4 dB per strip, which on its own doesn't seem too bad, but you multiply that by 8 or 10 or 12, and all of a sudden that's a lot of dB that you've lost in transmit efficiency. So Ian said, well, maybe we can extend this model that we developed and come up with a general solution for discrete decoupling or for these frequency selective surface decoupling. So that just came out last week, and it's sort of a extension of the original model. So you have a couple of driven ports, for example, for your 2 transmit loops, and then you model the coupling between them and any kind of discrete or distributed network. So the frequency selective components are distributed, but we allowed for the fact that you could actually have discrete elements as well. You model all of that, you can set it up in a matrix form, go through an enormous amount of horrible math, it comes out of the matrix, and you can actually optimize that matrix. You can use a few simple electrical engineering tricks. You can actually convert some of these into pi, these J networks into pi networks, and you can work through and optimize all of this. And you can actually come up with a solution for any arbitrary collection of coils placed anywhere, period. And that solution is optimized because the decoupling modes, whether the frequency selective surfaces or actual decoupling networks, can be optimized to have no coupling with each other or the coils themselves. And so, you have to pick some form of a filter. We pick the Chebyshev polynomials and go through and optimize that. But it's physically realizable, and it can be very simple. So here is that same circuit modeled. These are the reflection coefficients. So you see each coil, each of these 4 coils, is absorbing on resonance with no spurious resonances. You can also get a discrete, very simple discrete networks that will do the same thing. So the transmission, it's a band stop at the resonance frequency, so you've prevented propagation of a wave across this network. And I'll just leave it at that because otherwise I'm going to run out of time. 3 or 4 more slides. So I should say here, so this is a solution which allows discrete components to actually be used to decouple RF coils anywhere, anyhow, no problem. And the beauty of it is this is not lossy compared to this. So these kinds of coils have extremely high transmit efficiency compared to the frequency selective surfaces. So last thing I want to talk about is just stuff we've been recently doing on dipole trace. So I've alluded to the fact that at 7 Tesla, you're not working in the near field anymore. So you can't just use simple old Biot-Savart laws to calculate your transmit fields or your receive fields. Okay, you're actually working in a regime where you have to deal with near and far fields. It's actually the intermediate regime, which is the worst possible place if you remember all your EM theory. Because there's simple solutions for far field, there's simple solutions for near field, and there's the big mess of coupled Maxwell equations that you have to solve in the intermediate regime. So you can't get away from that. But because you're in this regime, antennas, so we've always called these loops, but now at high fields you can actually consider them antennas because you're looking at both near and far field properties. So dipoles have some advantages at high fields, which they don't at low fields. And so, again, dipoles as a transmit or a receiver have a problem in that closely packed dipoles still couple to each other. And there has not been a way other than distance to decouple dipoles effectively. The other problem with dipoles is, of course, in free space, a dipole, a half-wave dipole at 7 Tesla, is 48 centimeters long. So it's really long. It's way bigger than the object you're trying to image. So for the body, that's good. But for a head, it's not good. But that's in free space. In the head, as I mentioned, it's 13 centimeters. So the dipole can actually be shortened quite a bit. So people try to shorten the dipoles using inductors, capacitors, and various approaches that are all actually resistive. And they create all kinds of additional losses. So all the dipoles that have been used in MRI to date are actually lossy and not very efficient. So we took our approach where we can consider coupling. So these are shown as loops, but they can equally well be dipoles. And this is nearest neighbor, and then this is next nearest neighbor. But we know how to solve that problem now from the original IEEE paper that we published. So we can create networks, very simple networks, that correct for the mutual impedance between all elements in the array. Okay, second order, third order, fourth order couplings can all be done. And it turns out that those decoupling networks are very, very simple. They're a capacitor and an inductor. And we do it at 2 points, one at the top and one at the feed point. So the way we design our dipoles is not to take a dipole and put an inductor or something to shorten it electrically. We actually use meanders. So these meanders are much less lossy than putting inductive or capacitive elements in. But you have to be careful with meanders because you don't want to deposit extra RF power in the head in places that you might not know about. So we actually developed and published this model using covariance matrix adaptation evolution strategies. If you use CST, this is actually built into CST Microwave Studio, you can optimize the meanders from a perspective of SAR deposition in the head. And so these dipole elements, which will fit on a conformal surface, are designed to have optimal transmit efficiency, but at the same time, minimal SAR deposition in the head. And it's a convergent algorithm that we have to use. This is what the coil actually looks like. So this is a typical transmit overlapped, geometrically overlapped coil, and this is the dipole transmitter. And because you can make the dipole transmitter conformal, you actually improve its transmit efficiency just like you do for receive. So, and here's the decoupling network at the top, and then here's the decoupling network at the feed point. So this works very nicely. This is the conformal dipole. You get 8 beautifully separated transmit patterns compared to the loop, which even with your best efforts, has overlap. So the flip angle homogeneity, it's about twice as good. It's not the best color scale, and the reviewers pointed that out to us, so we're redoing it. But this is the loop, and this is the dipole, and this is about twice as homogeneous as this. When you use KT spokes, you can actually do very well with low SAR with the dipole. This is the other big advantage. So we are able to control SAR better. So this is the power being deposited in the brain, in the dipole, and in the loop. The loop gives you all kinds of little hot spots, which are very hard to predict, and which vary depending upon the phase applied to each transmit coil. Dipole's a bit better, and we do this by importing a discretized model of the human head from the Visible Human Project with all of the EM parameters that are needed. And we churn away in CST to get these. We'll skip this. The interesting thing about dipoles and loops is you can actually put them on top of one another. A, because they're intrinsically decoupled, so a loop and a dipole, when they're bisecting, are intrinsically decoupled. But because their B1 fields are different, you can actually extract closer to the ultimate SNR that you could ever possibly extract by superimposing on them. That's only ever been hypothesized, but we've now proved this because we had a way to decouple dipoles. So, in comparison to loop array, the dipoles have decreased power requirements for some of these homogeneity improving techniques. They have increased uniformity for transmission. They have higher reconstructed SNR in the middle of the brain, because near the surface the fields look very similar, but as you go deeper it changes. And they give you higher acceleration. I just have some eye candy here. So this is fMRI at 600 microns isotropic. These are only a few slices of a 300 slice volume. This is a problem when you go to high resolution. Now it takes a lot of slices. Cover a human head takes 300 slices. So you have to use multiband. This was done yesterday, so this is the first definitive proof that DTI at 7T is actually superior to 3T. Plus it proves that my tracks are still intact. So these are done at 1.5 millimeter isotropic resolution. With 2 different directions of encoding. I won't go into the details, but the structure for the tracks that you can get at 7T is really spectacular. So, the last few slides, just want to thank some of the people who contributed to this work, the shimming and the pulse programming work for Martin, Joe Gaddy, who's developed a lot of the protocols. So these guys all like high field. This is a Kilimanjaro. This guy was at Mauna Kea yesterday. This is at Machu Picchu, so I don't know what it is about high altitudes. The funding agencies, and just a little plug for students looking for postdocs and so on. We recently got a $66 million grant, as Chase mentioned. And we are looking for a lot of students, postdocs, and faculty. I got a CHR Foundation, as he also did mention, and I am looking for students and postdocs as well. So both in engineering and sciences. So with that, I'll quit.
All right, yeah, in fact, maybe just a couple of minutes for questions. The ECE folks, Scott? Yeah.
So your decoupling networks, just neutral inductance decoupling? No.
Sorry.
Are you decoupling out resistive coupling as well in there? I didn't think so. I didn't see any resistive portions in your decoupling networks, but
Most of the resistive coupling occurs through the sample anyways,
Yeah.
so we don't bother.
you don't try to decouple that. Okay.
So we're sample noise dominated.
Yeah.
17, so
Yeah.
not much you can do about that, but it turns out to be it's not that big a deal. When you have lots of coil elements anyways.
I guess just
Yeah.
small enough. Yeah.
Small enough.
Yeah,
There was one of the things you said was a little